In this discussion, we're going to introduce the plane wave solution to Maxwell's equations, and we're also going to see how plane wave propagation ties into what we know with transmission lines. So hopefully in a geeky way, this will blow your minds. So let's start out with where we left off with Maxwell's equations. Now in this case, we're going to look and see specifically what happens for these waves as they propagate through free space. So in where the wave's going to be going, there's no source or charge generating additional electric or magnetic fields. So we're going to start with the source-free version of Maxwell's equations. So we'll start out with del cross E is the curl of E is going to be equal to change in magnetic field, change in magnetic flux density. So there's the mu there. Separately, we also have the curl of the magnetic field is going to be equal to the change in electric field. And then also, since it's source-free, the divergence for both of these fields is going to be equal to 0. Now let's look at a situation where, let's just keep it simple coordinate-wise, where we're going to have E be in the x direction and H is going to be in the y direction. These curl operators can now be simplified to the curl of E. If E is only in the x direction, you'll have dEx dz, which is in the y direction, is going to be equal to the change in magnetic field in the y direction as a function of t. Both of these are in the y direction. And similarly, when you take the curl of h, you're going to get minus hy dhy dz in the x direction is going to be equal to epsilon dex dt, also in the x direction. So when you say that the electric field is polarized in the x direction, so the E field only varies with x and H field is all in the y direction, the curl now simplifies into a single derivative. So let's do a slight adjustment to pretty it up. So specifically, let's move that negative sign over, and then we're also just going to forget about let's just also forget about what direction it's in, since they're all in the same direction on both sides of the equation, so we can forget about the unit vector. If I call my Ex as the letter V, if I call my Hy as the letter I, and if I call my mu L, and if I call my epsilon C, and substitute that in here, you're going to find that this actually is the exact same form as the transmission line equations. So notionally, this is electric field and magnetic field, which is different than voltage and current. But mathematically, if you look at the way the equations are set up, they are the same. And so the solutions and the strategy that you can use to come up with the solutions stay the same. So let's remember how we ending up with the telegrapher's equations, which was how we found out this form of the solutions for the transmission line model. So first of all, if we call this equation 1 and equation 2, if I take equation 1 and take it with a derivative with respect to z, I get the second derivative of z is going to be equal to minus mu d by dt d by dz of hy. So just to review, this is taking d by dz of 1. And then if I take the other equation and do d by dt of 2, I get d of hy dz dt, oh, this should be a t, is going to be equal to minus epsilon d by dt squared of Ex. So now I have this expression for d squared dt dz. So I can substitute this in here and end up with the result that d squared dz squared Ex is going to be equal to mu epsilon d squared dt squared Ex. So this is a key result. Now if I do the same trick but swap the two equations, if I take d by dz of 2 and d by dt of 1 and substitute the result over, I'm going to get the corollary for the magnetic field. So d by dz squared of hy is going to be equal to mu epsilon d by dt squared hy. Now recall, this is the same as the transmission line equations, right? Remember the transmission line equations? We ended up getting the form where the second derivative of v is going to be equal to LC, the second derivative with respect to time of v. And then we also came up with something similar, right? d by dz of I is going to be equal to LC d by dt squared of I. So again, if you do this letter substitution, the mathematical formula is exactly the same, and so you end up with the same set of differential equations that you're trying to solve. So recall that here we had a variable of z and t. Same with the transmission lines. We had v and I related as a variable of z and t. So what we wanted to do was we did some substitutions so that everything is in terms of v, or everything is in terms of I. Or now in this case, we did the same manipulation so that everything's in terms of E and everything's in terms of H. And the final form is the same. It's the second derivative with respect to space is going to be equal to mu epsilon second derivative with respect to T. And what did the solution for that look like? Remember, in the most generic form, we defined it as a propagating wave, right? Where Ex is going to be equal to some forward wave of t minus z over vp plus a backward propagating wave of t plus z over vp, right? So if t and z are opposite signs, that means it's forward propagating. It's propagating in the positive z direction. And if they have the same sign, it's propagating in the negative z direction. And vp, which relates t to z, ends up becoming the propagation velocity. So this is an expression for any forward or backward propagating wave. Now remember what the next thing we did was, let's just look specifically at the case of sinusoids, right? So let's do the same thing with our electric fields. We're going to define an electric field in the x direction as a sinusoid specifically. So it's going to have some amplitude. I'll just call this some amplitude. It's a sinusoid, so we'll use cosine, and there's going to be omega t. So some frequency in time, kz, and k is just going to be my frequency in space, right? So one wavelength, in this case, omega is the number of radians that the wave changes for every unit of second. And over here, this is the amount of radians that the wave changes for every distance z, right? Plus a phase, phi 1. And then we'll also have the same thing for the wave going in the negative direction, right? Omega t plus beta z and plus phi 2. Now, if we compare these two equations and bend them so that one looks like the other, so that we can compare these with the propagation velocity, we'll find some key relationships over here, especially for this wave number k. So k we'll find is equal to omega over vp, or the frequency in radians divided by the propagation velocity. In free space, since the propagation velocity for free space is a constant, sometimes we might add a naught referring to what it is in free space. So if it's in free space, it's traveling at the speed of light, so it would just be omega over c. Or if you just pulled me off the street and said, hey, if you just pulled me off the street and said, tell me what k means, or I'll hit you on the head, my immediate knee-jerk reaction is k equals 2 pi over lambda. So if you plug in that omega is equal to 2 pi f and vp is equal to f lambda, you're going to end up with k equal to 2 pi over lambda. Usually that is my knee-jerk reaction to the definition of the wave number k. Now, before we leave the topic of k, recall that when we were looking at the transmission line equations, and we started out with our expression for forward and backward propagating wave, we plugged it in, compared the terms, we ended up finding that the propagation velocity is equal to 1 over the square root of LC. And so if we go through a similar exercise, you will also find that our propagation velocity is going to be equal to what? Remember, our letter substitution, mu is like L and epsilon is like C. So we will find that the propagation velocity for any medium is equal to 1 over the square root of mu epsilon. And so if you plug that in here, you also get another definition of K, which is it's equal to omega square root mu epsilon of the material. So to summarize, before we move on and take a close look at this in phasor form, I just wanted to point out how we got here. So we start out with Maxwell's equations. For the source-free version, we got rid of the curl because we didn't want to worry about the curl. So we just said E is only in the x direction, H is only in the y direction, which means that it will be propagating in the z direction. One of the things we'll point out later is E cross H is going to be the direction of propagation. But with that, you can simplify this curl into, the curl ends up just being derivatives with respect to z. And so when you rewrite it this way, you see that, hey, with some letter substitution, this is the same as my transmission line equations. And so following a similar derivation to what we did back in transmission lines, where we took the derivative of one way and the derivative the other way and did some substitutions, we ended up coming up with this rule where the second derivative of the signal is equal to mu epsilon, the second time derivative of the signal. So d squared by dz squared is going to be equal to some constant times d squared dt squared of that same thing. So that would be true for the E field and the H field. So we have the same form of the solution as the transmission lines, where it can be defined as either a forward propagating wave or a backward propagating wave, or a combination of the two. They would both solve the equation. And if we defined our waves as a sinusoid and we gave it, some generic phase, but also some frequency with respect to time, some frequency with respect to space, the spatial frequency we call K, and by plugging it in here and doing the comparison, you'll find these different definitions for the wave number K. And like I said, 2 pi over lambda is one that you'll come across pretty often. This form is also something that you might use a lot. And also the propagation velocity ends up being 1 over the square root of mu epsilon, just like it was 1 over the square root of LC over here.